Hi everybody. Today I'm going to discuss about the response of two degree of freedom system having free vibrations. Basically, the vibrating system which require two coordinates to describe its motion are called two degrees of freedom system. So for a system having two coordinates needs two equations of motions to represent the motion of the system. So to understand that, I have taken two storied frame having loads on the floors, and we can idealize this building as a single column having concentrated mass at the floor levels, these floor levels and these floor levels, with the understanding that only horizontal displacement of these masses are possible. As I said, loads on the two floors, I am giving equivalent masses M1 and M2 on each floor. In other way, I can say these masses M1, M2 are depicted as lumped masses at respective rigid floor levels. So 2 degrees of freedom, as this frame has 2 degrees of freedom, that is the two horizontal displacement at floor levels. And joints between girders and columns are fixed against rotations. That is why there is no rotation of a horizontal section of the level of the floors. We need to understand this. Another important points, all are what I am telling right now, all are the assumptions. So another important point is slab or girders on the floors are infinitely rigid as compared to the columns. Now, at any time or any time instant t, these masses are acted upon by, say, forces F1 and F2, which causes displacement. Those are x1 and x2 respectively. Now, when a floor displaces laterally with respect to the floor below it, if this floor displaces laterally with respect to the floor below it, right away a resistive force or resistive shear force, here I have written Fs equal to Kx, is induced in the supporting columns, which is proportional to the lateral displacement. Here I can see the inertia force, because I am finding two forces, inertia force, and already I discussed about restoring force. So these inertia forces, it is mass and accelerations. Newton's second law of motions. Also using Alembert's principles, we can find this inertia forces. Now let's move to see how we can represent this in a spring system also, because let's see, first bring the diagram, then we'll understand it very clearly. About this first one, I mean two-storied, this frame already I discussed, as well about the system resistance and inertia forces. So what I have done here, I represented here in two ways. First one, as I said, a single column model representations of a shear building and free body diagram. Shear building and free body diagram. Second one is multi-mass spring model representations of a shear and free body diagram. But both are equivalent. Consequently, the equations of motion for the two-story shear building can be obtained from any of the free body diagram. How? By equating to zero the sum of the forces acting on each mass. We can see here what are the forces acting on each mass, as well here also we can see what are the forces acting on each mass M1 and M2. So let's move ahead to go or to understand in depth of it. Equations of motions for each mass at any instant t. We can write this equation for first mass and this one for the second mass, M1, M2. We can see here M1, M2. This is with the acceleration, so it is inertia forces. This is restoring force with the K and displacement. And already I put here the directions. According to the directions, there will be plus and minus. So once we get the equation, surely we can write, rearranging the term. The equations in matrix form are. How to get that? We have to get the mass matrix, and then regarding mass matrix I want to say something. This mass matrix, it is a diagonal matrix. Non-zero elements are only in the main diagonal. Stiffness matrix elements are designated as stiffness coefficients. As well, here I have taken displacement vector. You can see here this x1, x2, acceleration vector with x1 double dot, x2 double dot, and force vector f1, f2. Now, using this matrix, I mean this matrix equal to M, this equal to K matrix, this equal to X, these vectors. So equation in matrix form we can write like this. So we got this. Now this is the equations. We have to do something on it. What to do? Because if we think of the problem of free vibrations, if the problem of free vibration, it means what? It requires this F vector must be 0. That is important points. So let's move in the next slide. Considering this force vector is 0 because we want to get the problem of free vibrations. So what will be our equation then? So let's move. As I said, this will be say natural frequency or natural modes. Why I wrote this? Because my target is to find natural frequencies and natural modes. So for a system, as I said, for free vibration, force must be equal to 0. So I put here 0. Now the resulting equation in matrix form we can write like this. Because this position M vectors, we put the mass matrix, and this position is stiffness vector, we can put here stiffness matrix. And this also we put here vector here, x1 double dot, x2 double dot, this is acceleration vector, this is the displacement vector equal to 0. So what is our target now? Because we want to solve this. To solve this, so we need to know one important things. For free vibrations of the undamped structure, we seek a solution in a certain form. So what is that form? Like this. A sin omega t minus alpha. Now if we do differentiation twice, it will be x double dot, I mean acceleration. And right hand side will be like this, minus omega square. So once we get this, so we have two equations. One is in terms of displacement, another is in terms of acceleration. So putting these two equations here, what we get? Look at, I get this. Because this acceleration vector here we can see this one, it will be this one, and then k, but what I did, this sign term coming for both cases, but I have taken this out as a common factors. Now system of 2 degrees of freedom can be expressed as this. Already we know how we got these equations. So what we can do now, factoring out this sine omega t minus alpha, factoring out and rearranging. K will be here and minus omega square m will be on the right hand side, and this will be as it is, and we are taking this out. So our equation this. That's why I wrote factoring out and rearranging. We can write this. So what you can do next? This. The formulation of this equation. Formulation of this equation is an important mathematical problem which is known as Eisen problem. And its non-trivial solution, that is, the solution requires that the determinant of matrix factor of this, determinant of the matrix factor of this be equal to 0. It means this determinant must be equal to 0, but here I have written AI is not equal to 0. It is very important because it is non-trivial solutions. It has relation with this one. That's why I have written here. So we got the determinant of the matrix factors, this one. Now our target, the expansion of the determinant in this equation, it yields an algebraic equation of nth order in omega square, which we called, or which is known as characteristics equation. So let's see in the next slides how to do the expansion of this determinant to give us a quadratic equations in terms of omega square. So this was our equations. So what you can do here, say omega square, as I said, eigenvalue, I am considering equal to lambda. Because if we consider this lambda, so once we get the quadratic equation, it will be very easy to handle that. So what you will do, equations can be expressed. How? This one. How it comes? Very clear, K and M matrix we know. So very easily you know K1 plus K2, we can see here K1 plus K2 minus of this mass matrix. So here it is M1. So M1 will be here, and there is a lambda square, I mean omega square, so it is lambda, so it will be lambda here. And here there is a minus K2, minus of 0, it will be minus K2. So here minus K2, here will be K2 minus M2 lambda. Same way, subtracting this matrix, and replacing omega square equal to lambda, we get these equations. Now let's move how to solve this to get the quadratic equations. So to get quadratic equations, we'll try to make it more shorter. I mean element to be more shorter in a sense that considering k1 plus k2 equal to p and k2 equal to q. So equation can be expressed as this. Because here it was k1 plus k2, I consider it as a p, and here it was k2, I am considering it as a q. So equation take this form. Now, as I said, we have to get a quadratic equations. So from this, very easily we can find a quadratic equations. This is actually, as I explained, how do you got this? Say k1 plus k2 equal to p, and this is k2 equal to minus q, so surely we are getting this same. Now, a quadratic equation in lambda square, as I said, we change to omega square equal to lambda. Otherwise, here it would be omega to the power 4. So to get exact shape of the quadratic, so I mean as we know our quadratic equation, general equation we know very simple one, ax square plus bx plus c. So here lambda square, this is lambda and this is the position for c. So now it's very easy to handle that. So there are two roots. How to get those two roots? So surely we can write two roots can be expressed as this. So we got the two roots. But our target is to find the omega. So what we will do? We'll bring the relations because we considered lambda equal to omega square. So surely omega 1, omega 2, it will be a square root of lambda 1 and lambda 2. As we understand that the structure having 2 degrees of freedom will have two eigenvalues. Two eigenvalues, this omega 1 and omega 2. Vis-a-vis time period also. So what will be that? Like this, t1 and t2. So from this concept, 2 degrees of freedom, we got two eigenvalues. So why not we say that a structure having n degrees of freedom will have n eigenvalues as well as n modes. And also we need to understand that each of the degrees of freedom is attributed as a mode of vibrations in parlance of structural dynamics. That is very common thoughts. So structure having n degrees of freedom, also we can say n modes. So let's move to see that or how to find that. Now we got here natural frequencies and time periods. So here, as I said, 2 degrees of freedom, of course it has two modes. So what will be the first mode? So considering the first mode like this. In this case, how to get that x1, x2? Important point, this is of course a homogeneous equation, right hand side is 0. So what we will do here, say considering x1 equal to 1, we can calculate x2. Very easy to find it. In case of mode 2, I mean second mode, we can do the same thing, only the difference here x1 equal to 1, here x2 will be equal to 1, so we get x1. So we got x1, x2 for the first mode. For the second mode also we got x1 and x2. So let's see how to arrange these four values, because as we understand this x1, x2, what we computed from here, we can call it as a eigenvectors of this problem. So how we can depict it? As I said, we have the value of x1, x2, and I said it is eigenvectors of the problem. So surely these four, we can depict it as this one. Here this phi, it is termed as scaling vectors. Very important point to understand, it gives us a measure of in what ratio the displacement will take place in relation to one another under the application of an externally applied dynamic force. This is a unique property for a particular structures. I think what we studied till now, it is enough to explain this response of 2 degrees of freedom system. I think we are done.